speaker is Vindhya Vashishth, and she will be speaking on hysteresis of the large-scale dynamo in the presence of the small-scale dynamo. So Vindhya, can you share your screen?
Yeah.
Thanks.
Able to see my screen?
Yeah. Yeah. Please go ahead. Yeah, make it full screen, I think.
Now can you see the full screen?
Yeah, yeah. Perfect.
Okay. So hello everyone, I'm Vindhya Vashishth from IIT. So I'm here to present my work on hysteresis of the large-scale dynamo in the presence of small-scale dynamo. I'm quite new in this pencil code, so I'm just showing my preliminary results, like what I have done so far using the pencil code. So these are the contents of my presentation. I'll initialize by explaining the large-scale dynamo for the sun. Then I'll discuss about the dynamo hysteresis, and then I'll explain briefly about my previous work that I did on the axisymmetric mean field dynamo model, and I'll discuss the results. Then I'll discuss about the small scale dynamo and the alpha omega dynamo model that that I have used using the pencil code, and then I'll discuss the results and then the conclusion. So as you can see in this figure, the sunspots, the butterfly diagram, solar cycle, all these are the manifestation of the large-scale magnetic field of the sun. And it is expected, or it is believed, that the large-scale magnetic field is produced by the large-scale solar dynamo that is operating in the solar convection zone, in which the convective flow of the ionized plasma is responsible for generation of the magnetic field and magnetic cycle by the process called dynamo. Now, in this dynamo, there are two important parameters, namely differential rotation and the helical convective flow. So, first of all, I'll explain the differential rotation. Now, due to the differential rotation of the sun, this poloidal field gets stretched in the toroidal direction, or we can say azimuth or the phi direction, and hence give rise to the toroidal field. This process is the omega effect. On the other hand, when these flux tubes rise due to buoyancy and twist due to the Coriolis force of the sun, basically gives the loop. These loops are there in the poloidal plane, and due to flux cancellation gives rise to the toroidal field. Now, there's another important factor, or we can say a process that is observationally supported for the generation of poloidal field from the toroidal one. It is namely a Baku-Clinton process, which involves the action of tilted bipolar sunspot pairs that arise due to buoyantly rising and twisted magnetic field. Now, when this tilted bipolar sunspot decays, the polarity of these sunspots gets more diffuse in the high latitude, and they form loops in the poloidal plane. So, when this gives rise to the poloidal field in the solar surface. Now, important parameters that govern the dynamo is called the dynamo number, which is given by alpha del omega r by eta square, in which alpha is a measure of helicity, delta omega is the angular velocity, r is the radius, and eta is the turbulent magnetic diffusivity. Now we need to understand the trend of dynamo number with the magnetic field strength. As I've shown in the figure, this is a cartoon diagram of the relation between dynamo number and the magnetic field strength. As you can see, there's a transition region, which is called the critical dynamo number. Below the critical dynamo number, the dynamo does not operate. The magnetic field decays, whereas above the critical dynamo number, the magnetic field gives the oscillation and the dynamo starts operating. Now, this pattern which I have shown is basically obtained when we initialize the dynamo with a weak magnetic field. But when we initialized the dynamo with a strong magnetic field, for example, if we'll give the output of this magnetic field and the input of the next field, then we get a strong oscillating function even when we before we were getting a weak magnetic field. So this pattern is known as a hysteresis. This hysteresis curve. So this dependency this behavior was studied by Kichatov-Olimsky in 2010, in which he basically used the idealized mean field model with the helical alpha distributed over the whole convection zone. Then Kichatov and Brandenburg in 2015 studied the same behavior, but they did the 3D simulation of large-scale dynamo on the helically forced turbulence. So inspired by this work, my previous work was using the axisymmetric mean field dynamo model, but I used the Bacco-Clinton alpha to study the hysteresis curve, in which I used the basic toroidal field and the colloidal field evolution equation, in which this is the source term for the toroidal field, and colloidal field source term is given by this. Now, this source term is a very idealized form. We have done a very idealized form, which is denoted by alpha T. This alpha is the Bacco-Clinton alpha that we have used, and this magnetic field is the average magnetic field in the base of convection zone. Now, we have also introduced the magnetic field dependency, the turbulent diffusivity, as well as on the alpha, the Bacco-Clinton alpha that we have used. This was inspired by Kichatov and Olimsky 2010. So, in which they use the analytical form of the turbulent diffusivity and the Bacco-Clinton alpha and given by this. So this is basically the magnetic field dependent quenching based on the quasi-linear approximation as done by Rudriger and Kichatov 1993 and Kichatov et al. 94. Summarize these two figures, I've just shown you the limits of these magnetic field. So the beta, as you can see, is basically the magnetic field normalized with the equipartition field. So when this value is greater than 1, so I'll explain the hysteresis, like why we are getting hysteresis behavior. When we initialize with a strong magnetic field, then the diffusivity and alpha inversely related. So the dynamo number is basically large, as you can see here. Then it decays, of course, but when we initialize the code with a weak magnetic field, then the effective dynamo number is less. So we got hysteresis curve from our model, in which this blue curve I'm showing is the simulation and started with a weak magnetic field, the weak seed field. So as you can see, the subcritical region, it's showing the decay field. This plot is the butterfly-like plot of the toroidal field. Now, in the supercritical region, we say a strong oscillatory function, or we can say a strong oscillatory field, that is, the dynamo is operating. But when we give the final seed field of this quantity to the initial field of the next quantity, then we observe that instead of decaying, it is given a strong oscillatory function, or the dynamo is operating. As you can see in this figure, we can see operating dynamo in this region. So now I'll explain the small scale dynamo. Since the sunspot, the radial magnetic field, these are associated with the large scale dynamo, as I've discussed before. But you may see there are some field that is always present, independent of the solar cycle. And in fact, it is present in the solar minima. That means it is produced from a different mechanism. It is expected that this carpet magnetic field is produced by a small scale dynamo. Now, what is a small scale dynamo? So it is generated by the 3D random velocity field that is exponentially grow a seed field via stretching, bending, twisting, folding, and without any requirement of net helicity. And why we call this a small scale? Because the length scale that are dealing with a small scale dynamo is very smaller than the size of a system, or we can say is smaller than the forcing scale of the flow. Now, in small scale dynamo, it works when the Reynolds number is above a critical value. Now, in sun, we know that the Reynolds number is very large. So it is expected that the global, or we can say the large scale dynamo or the local dynamos are expected to operate in sun at the same time and location. And in fact, previously it was studied by Bharat and Brandenburg 2016 and by 2016 that small scale dynamo may affect the presence of large scale dynamo. So this gives a new motivation to check like whether the hysteresis behavior that we studied in the axisymmetric mean field model, is it valid, or do we see this behavior in the large scale dynamo in the presence of small scale dynamo or not. So for that, I have used the pencil code in which our model consists of isothermal and compressible fluid, which follows the equation of state. And in this framework, the momentum equation becomes is in this form, the basic continuity equation and the induction equation. So the d by dt, as I've shown here, is basically del by del plus u plus us. Now this del here is the advective derivative, and the us that I have shown here is the imposed uniform large scale shear flow, and s which is used here is the constant shear rate. And this bold s is the traceless rate of strain tensor. Now in this momentum equation, the turbulence sustained by supplying the energy to the system through a stochastic forcing function, and which is random in nature. So the forcing function of this transverse wave is given by this. Now in this n is basically to normalize and is given in this form, and at each time step, the wave number, as you can see here, that randomly takes any value from all the possible wave vectors around a given forcing wave number. Now, this k is basically the Fourier coefficient, Fourier amplitudes, and it is given in this form. As you can see now, this r is dependent on this sigma. This is important in our simulation, as this is a measure of helicity of the forcing. Now, for studying the hysteresis behavior, we need simulation at different points. So for that, we'll change the sigma to evaluate the dynamo transition as well as the hysteresis behavior. Now, let's discuss about the results that I've got from that. As you can see, as I've shown previously, the dynamo transition, we also see the dynamo transition in this case where the small scale dynamo is present with the large scale dynamo. And this figure shows the relation between relative helicity and the toroidal magnetic field normalized with the equipartition. As you can see, there's clearly a critical point. Now, this URMS, as I've shown here, is the RMS value of the velocity at statistically stationary state. It is obvious to see, like when there's in subcritical region, this velocity is high. Now let me discuss about the butterfly plots and the time series plot that we got from this figure. This is the subcritical region. So this is the butterfly plot of the toroidal field, and this is the time series plot. Now, as you can see, this shows a very less magnetic field. Whereas when we see the same plots for the critical value, then we see the dynamo is operating. It is clearly seen from this. But now, if I discuss about the small scale components, there's a small scale magnetic field. So basically, this is in small scale energy density that now we are dealing with. It is the residual of energy density and the large scale, because it is quite complicated to find out it separately. So what we have done is that we have just find out the residual of the total field, total energy density we have, and the large scale energy density. As you can see here, clearly, that in when there was no large scale dynamo operating, the small scale dynamo still operating. Whereas now we'll see the same component for the point where where the dynamo was operating. So we'll see such behavior, in which I think you may notice that there's some cyclic behavior. There's an interesting point to note that here magnetic field is not purely from the small scale dynamo. There is some contribution from the large scale as well. It's simply due to and shredding of the magnetic field that is affecting this field. So now this was the simulation when we started with weak seed field. Now, when we started with the strong field, we noticed that the curve change, that trend change, or we can say the path it needed to take previously, it changed. As you can see, the point where it was decaying earlier, now it's showing us, now the dynamo is operating at that point. So show the butterfly plot for this, you can clearly able to see the dynamo is operating this region, and you can also see with the time series plot. Now I'll show the small scale dynamo in for this also. So first I'll complete this for the large scale dynamo. As you can see, there are still some points left in between, but I have this simulation for the last point. So I am just need to complete like in which point, like in this point in which the dynamo is basically giving the critical value here, but we'll get the essence of hysteresis from this plot. Now, if we'll see the small scale components for this only, we'll able to see that this small scale component is clearly affected by the large scale magnetic field in our system. Now, we have evaluated the dynamo number in this form where and the alpha and the eta are basically governed by the test field methods, the pencil code. Now, we're clearly able to see that when the helicity is less, the dynamo number is less. So it is hard for the dynamo to operate. Whereas above a critical value, the helicity is large. So the dynamo is easy to operate in that region. So if I'll conclude, with the help of pencil code, we have set up an alpha omega dynamo simulation which excites both large scale as well as small scale dynamo. In this dynamo, the fluid is helically forced and large-scale linear shear is imposed. We observed that the dynamo transition and the hysteresis of the large-scale dynamo in the presence of small-scale. We also studied the dependencies of helicity, diffusivity, dynamo number, small-scale field, and the large-scale field with the relative helicity. Thank you for your time. Questions are really welcome. Thank you.
Okay, thanks, Vindhya. So the floor is now open for questions. So we have about 10 minutes. So please go ahead. Yeah, so I immediately see one hand. Axel, please.
Yeah, thanks very much, Vindhya, for a very interesting presentation. I would really like to read more on that. So you find at the end that both alpha increases, but also eta t decreases much more rapidly. So it is, of course, extremely interesting. Have you actually observed any connection with changes in the flow at that point? How does the flow actually really look like? And what could that explain, or could you understand somehow why there is such a strong decrease in the magnetic diffusivity so suddenly?
The critical value you are talking about.
Yes.
So
Eta t, the blue one.
Okay. So you do you need to know the trend for dynamo number or the diffusivity?
Diffusivity.
Okay. So
as we can I see that like alpha is also actually decreasing. Yeah, but dynamo, yes, right. Okay, but alpha is, the dynamo number is increasing. Both are then decreasing. I see that now. Yeah, any connection with the changes in the flow, right?
Interesting. No, we haven't seen basically the change of the flow, but what we noticed, this butterfly plots only. Like at the critical value, we are getting operating dynamo, and from just below the critical value, we didn't get any dynamo operating, or the magnetic field decays. We observe that. And there's one interesting thing that we observe here, but we are still working on that. I shall show you that. If we'll see this figure, the diagonal component of the alpha that we evaluated in our code, we saw that after a critical value, the alpha 11 keeps on increasing, whereas it decreases. We are still basically thinking like, why did this happen? We're in middle of evaluating the results.
Yeah, that's very interesting. Yes. So that really begins to shed some light on the whole thing. Thank you. That's so great.
Our next question by Simon.
Yeah, interesting talk. Thanks very much for that. So I was wondering about one thing. So when we talk about hysteresis, usually we also interested in sort of the behavior when it's going back. So in your case, from a large dynamo number, from a actually working dynamo, back to a small dynamo number, if it's actually able to keep it up. Have you performed any simulations with that, where you start with a large, strong, a relatively strong initial field, and then develop the dynamo? And actually, sorry, I misspoke. Actually, you start with a small field, weak field, have a dynamo, and then reduced slowly the relative helicity. Sort of exactly in this plot. So if you're on the right, on the red branch, right, you're there on top right, and then you reduce your dynamo number or your relative helicity, your forcing. Do you actually see that where it goes back? If it goes back through the red curve, or is it going back through the blue one?
So actually what we did here is that all these simulations, they are independent of this. For example, I started with a weak field, right?
Yes.
Now when we get this field, so the output will be strong. The dynamo is operating in this field, but we saw like here in this subcritical region, the dynamo is not operating. So if we give the output of this field, the input of this field, then also dynamo would decay, because the output is also decaying. But the output also we are getting decaying field. If that will be the seed, if that decaying field will be the seed of the next output, it will also decay. It will act as a weak initial field only.
Yes, but I guess if you start with a weak field with a high dynamo number, you will, you're on the top right.
Yeah, so that we did in a symmetric dynamo model. Like here, this is a if we'll start, then we'll decrease. It will follow this blue curve only. But if we'll start with strong field, then only the path will change.
Okay. So it's slightly different than the hysteresis in, say, a magnetized material, where you would actually go back through the yellow curve rather than through the blue curve. Okay. Okay, interesting.
Could you maybe show again, how does the circle look like? Vindhya, could you just somehow get, now it's also confused by it. It normally should go like in a circle, right?
Yeah.
Is it not? Yes. Now if you go with your mouse, yes, now down, and then you go to the right. Yes, and now you increase again. Yes. Oh, and then it goes up. But why does it not go up on the red line?
Oh, that is not.
Why does it not go up on the red line? I would have thought it goes up on the red line, as Simon probably also was thinking.
Yeah, exactly.
Are you asking?
So how do you get the red line?
This red line. This red line is basically from the simulation that we started with a weak field.
Yeah, but the field I thought becomes weak also when you go on the blue line and you drop below the minimum relative helicity value, and then you drop on this point. Yes, exactly. Yeah. So then you are in a weak field, are you not?
Yes, you are right. So these are the these must be two other points here, or one we don't know yet because the code is still running. There should be a curve in between the critical value that we'll get in between this. So there must be a value here, but I know for sure that we have done a simulation that at this point we'll start from the strong magnetic field, the strong input field, then it is decaying. So dynamo is not operating at this point. That we are sure, but for the exact which point it is stopped operating, that we need to find yet.
Okay. Okay.
Okay, Piali, you have one question?
Yeah. Okay, thanks, Vindhya, for presenting your nice work here. I am just curious about what is the relation between this relative helicity, which is a parameter, I think, in the
Yes.
parameter you are tuning, to the strength or strength of the small scale dynamo. So it should be independent, right? So is it?
No, there is zero.
There is no small scale dynamo, relative
There is
helicity.
no helicity. There is no helicity.
But does small scale, yeah, there's no helicity, but does the small scale dynamo require helicity?
No, small scale dynamo does not require helicity.
Yeah.
It works independent of the helicity.
So you still have, doesn't matter what the relative helicity is. The relative helicity is only changing the fact that you have a large scale dynamo or not, right?
Yes. So, so
The
actually,
small scale dynamo remains the same throughout all these.
no, actually, as I mentioned, like the small scale dynamo affects the presence of large scale dynamo, and it's a vice versa case also, that large scale dynamo may affect the small scale dynamo. Because when we have a small scale dynamo, then that small scale flow is there, that is the Lorentz force, and the small scale convective flow that will affect the angular momentum transport, or we can say turbulent diffusion will change. So there is a both case, like small scale dynamo presence will affect the large scale, and the large scale also will affect the small scale. Both the cases are there.
Okay, and the hysteresis
is different.
So this hysteresis, if the hysteresis exists or not, so what does it depend on? Is it this coupling between large scale and small scale, or what is this hysteresis dependent on?
This hysteresis depend on basically the magnetic field strength that we are initialized with. This is the path dependent. Now, if I just wanted to say, like, even if there's a presence of large scale, there will be a small scale, and even if now the small scale dynamo decays, but we'll still observe the small scale. So small scale dynamo is always present in our model.
Okay. So the hysteresis does not have anything to do with the small scale dynamo, or does it?
Okay, so hysteresis behavior must be affected. For example, if we'll involve the large scale, so the curve would shift a little bit here, a little bit there. There will be shift.
Okay.
There will be shift.
Okay, thank you.
So we have one more question from Matthias. Matthias, please go ahead.
Yes, thank you for the talk. I have a few remarks.
Yes.
And so I would not be able to claim that this is reflecting a consensus, but at least in our group, we would frame it in the way that to say, for instance, that it doesn't make sense to say that the large-scale dynamo acts on the small-scale dynamo, because how would we define a small-scale dynamo? We would say it is the magnetic field, which is self-excited or self-generated in the absence of a mean field. Otherwise, we would not be able to define what a small-scale dynamo is. But
Yes.
given this definition, there is no way that the large-scale dynamo acts back on the small-scale dynamo, because it's just the absence of the mean field which is necessary to be able to define it. And next remark, in our experience, helicity is not, no, it's not our experience, it's general wisdom that helicity is not required for the small-scale dynamo, but it's not true in our experience that helicity does not affect the small-scale dynamo. What we see is that if you provide helicity and suppress the mean field artificially, but this is allowed because the mean field dynamo is an instability. And you could always argue, let us, at least theoretically, select an initial condition such that the mean field dynamo is not excited. We would still see some dynamo, namely the small scale dynamo. So the suppression of the mean field is not really a forbidden experiment. But then we see that the small scale dynamo, under the condition of helicity provided develops larger scales than without helicity. And that's why it is easier to excite. So helicity helps, and we name the scales on which it works then mesoscales, because they are not necessarily as large or as small as the velocity scales, or smaller than them. Then they can be bigger than these velocity scales, but still it's not a mean field, because a mean in these experiments is usually defined as an average over 1 or 2 coordinates. So that's why I think it's really a fact that helicity supports the small-scale dynamo. And then a remark: if you think that the small-scale dynamo has really an important hand in what's happening, then we must be careful when applying test field methods, because the standard test field method, including the axisymmetric module, the pencil code, they would not be able to reflect that hand. And yeah, the question was already asked in a sense, but I would, so it's a remark or a question, what you like. In my feeling, the basic effect in the hysteresis is the quenching, or the not identical quenching of alpha and eta. And that would also happen without the small-scale dynamo, right?
Yes. Yes.
Have you done
Yes.
that experimentally without a small-scale dynamo, still seeing the hysteresis?
Okay, so this model, or basically this simulation, was done in 2D simulation that I have shown previously. In 2D, we have shown that, but not in 3D. In 2D, as I've shown here, in axisymmetric kinematic dynamo model, we are able to see in which only
So
large field is present.
So this is without the small-scale dynamo, but it's a mean field model here.
Yes, it is mean field.
Yeah, but that is not the ground truth. The ground truth would be a real forced turbulence simulation, but without small-scale dynamo, as you did in the other experiments. But would you still see the hysteresis? I would expect so, because if the quenching ideas are correct, then they would work similarly, even without the small-scale dynamo, and then we could have that effect.
Yes.
But have you verified that?
Okay. So I guess in Kara-Kichatonov, Brandon, 2015, they did this simulation of large-scale dynamos on the helically forced turbulence. This was without small scale.
So was it so in that paper that the Reynolds numbers were always too small for a small-scale dynamo? Was it so? I don't recall the details of that paper.
That I need to check.
What was the question, Matthias?
What the Reynolds magnetic Reynolds number was in that paper? Was it guaranteeing that there is no small-scale dynamo?
There was small-scale dynamo.
Yeah, and that's exactly my question. What would happen with the hysteresis without the small-scale dynamo?
Okay, I also don't remember now, but I think it was large, like 100.
Yeah, that's what I expect. That normally the Reynolds number would not be so tiny.
Yeah.
So that's for me a bit of an open question, whether is the small-scale dynamo only a modification of the hysteresis, or is it essential for it?
Yes.
Okay, thank you.
Okay, thanks, Matthias, for your comments and remarks. So I think we will take a short break now for about a little more than 20 minutes. And we will come back again for the next session. So in the meantime, I would still encourage all participants, if they have any questions, to put it on the Slack channel. And I would also ask the speakers of that session to kindly go and have a look at the Slack channel if they have any pending questions to answer. So we'll be back in 20 minutes then. Yeah, slightly more than 20 minutes.
Slightly more than 20 minutes. And let us know. So after we come back, there's a talk by Shohel. But the slot after that, I mean, it's still open. So anybody wants to present anything or talk about something, you're welcome to fill up that half an hour slot. That will be after Shohel's talk.
Could somebody check the thing that I uploaded? It looks like that's just a link, right? Which of course works at the moment.
What link?
So on Slack, I uploaded
Yes, yeah.
something which I was hoping
Yeah,
was
yeah.
actually
Okay,
the PDF
okay,
file,
your
but I think it's just a
presentation.
link. Am I right or not?
Yeah, it works. I can see it. Wait, yeah, I
Yeah,
can
it
see it
works.
now. Yeah. That has 12 pages.
But how do you know? The name is certainly the link,
It's
but
a
it
PDF
could still be a
file.
PDF file. Can you
It's a
check?
PDF file. It's a PDF file.
Right. What I meant is, if I suppose I remove the link, would the thing actually be uploaded? Would it have been uploaded, or is it then gone?
Okay, you mean is it uploaded on the Slack or not? I don't. Okay, so you can try removing it. Have you?
I mean, the idea was not. The idea was to have actually the PDF file uploaded on Slack, you know? Or what,
Yes, yes. That's what.
Yeah.
Okay, what I could do, and then we couldn't check, of course. I can just.
That should be possible, right? Because I uploaded an image or something and it got.
You could upload an image.
Yeah, this one I uploaded. It's a long.
You can just upload as a PDF file.
Yeah, I can do that. But let him, but otherwise people won't do it. Just please.
So now I've moved it into a subdirectory. Will it still be there, or will it now be gone? Let me check.
It should not work.
Yeah, now it's not found, so I have to move it back.
So is it too? How big is it? I mean, you